Welcome to lecture number 19. Today we are going to talk about dielectric materials. Let's connect as to what we have been talking about. We started with metals. We started with the metals, in which we started looking at conductivity of metals. Then we moved on and we talked about effect of periodic potential in a lattice, which eventually leads to a band gap. Consequence of that band gap was that we got materials which were semiconductors. Why were they semiconductors? Because their conductivity was lower than that of metals. And why did this happen? Notice that insulators will be very closely related materials to insulators. So just before we start talking about today, we are going to talk about dielectric. Since we are going to talk about dielectric materials, we are going to talk about materials that do not conduct, that they are insulators. But to connect it back to semiconductors, what had happened was that, recall EK diagram for a semiconductor, it looked something like this. If this was K, there was a on this energy axis, and this was the K axis, and in this axis we had a valence band. This was the valence band. If we looked at 0 K, temperature which was 0 K, then we had that this place was full of electrons. There were electrons everywhere. Valence band was full of electrons, whereas conduction band, which is this higher band up here, this is the conduction band, this is the conduction band, and this is the valence band. This was all valence band, and this was the band gap. This was Eg. So if I look at like this, on this side as something like Ev and Ec, and a band gap here Eg, then what happened was at 0 K, this material, this semiconductor, was also insulator. Why was it insulator? Because valence band was completely full of electrons all the way to the top, whereas conduction band right here was completely empty. And what that meant was that neither there could be, since there were no electrons, no carriers in the conduction band, there could not be any conduction due to conduction band. Similarly, in valence bands it was completely full of electrons, though there were charges, but there was no space, no energy state for electrons to move around, and hence even they could not conduct, and this material therefore was an insulator at 0 K. Only at some slightly higher temperatures electrons began to jump when the thermal energy was sufficient to overcome this band gap. Some electrons from here jumped up here, some electrons got jumped here, leaving behind holes, and they left behind holes where there were still many electrons left here. Now these holes in valence band conducted, these electrons in conduction band conducted. Overall we got some conductivity out of these materials, and these were semiconductors. These were semiconductors. Now what happens if this band gap was very large? Remember, in silicon this band gap is only 1.1 electron volt, whereas if you go to diamond, then this band gap becomes something like 5.3 electron volts, very large band gap. What happens if this Eg is very large? Then in that case, at nominal temperatures, so let's draw it like this here, this is Ec, this is Ev, and a large band gap, Eg, and a large band gap, which is, this is large. Then remember, these electrons which are here are not going to be able to jump up here. This jump will be very difficult, and hence again these materials will not conduct, and these will be insulators. These will be insulators. So in other words, there are materials where we have charges, but they are bound charges. They are not free. It is only free electrons which conduct. Once the electrons or holes, they are able to conduct only when they are free. But if charges are bound, then they are not going to be able to conduct. Now if you apply electric field in a metal, the charges are able to move over long distances and you get conductions. But because in insulators and dielectric materials charges are in their bound state, the consequence would be that they will not be able to travel and you will not get conduction. You may be inclined to neglect these charges completely because there is no conduction, but that will be a mistake, because what Faraday discovered was, if you had two parallel plates, something like this, and if you are connected to a battery, and you inserted these materials in here, such materials in here, something happened. That something which happened you have learned in your 12th grade or earlier before also, which I am going to repeat again. But before I do that, I want to establish the importance of these materials, which is why we have shifted from semiconductor to dielectrics. If you don't believe, then capacitors you have seen, of course, all around, this capacitor materials. Those are dielectric materials. They are supposed to not conduct, but provide some capacitance, and that term you are familiar with, and hence I am able to use it. But if you look at, for example, take your computer, take out a chip and cut it out, look at in a SEM, scanning electron microscope, where you can see small sizes or even transmission electron microscope, you will see that devices are full of materials that are insulators and what we call as dielectrics. They are same material, same class of materials. Since you are familiar with dielectric constants, then I am inclined to use those also, though I will go through them in this lecture as well. But when I said if you cut out a microelectronic chip and you start looking at SEM, you will find insulators, meaning thereby these are low K materials, low dielectric constant materials, which are there for single purpose, that they provide insulation from one device to another device, one layer to another layer. In addition, you would have dielectrics where K prime will be large, and the goal of these dielectrics will be to provide large capacitance. That means the circuits would be using capacitors themselves, and hence you would like to use K prime which is large. So notice that though we are using the terms insulators and dielectrics, but at level of understanding a material there is no difference except large K prime or a small K prime, meaning dielectric constant. And if we understand what is the origin of this K prime, then it does not matter whether it is insulator or dielectrics, we will deal them as one class. So with that background, let us look at this experiment which we talked about. This experiment, if you insert a dielectric here between two electrodes, here the two electrodes are, and between them you are inserting a dielectric material. What happens? Let us look at that. But let us start with in vacuum first. Let us start with what happens in vacuum, and what I am doing now is something which you are familiar with over some time. You have done that in 12th grade also, and also your first year physics, etc. And so I am basically repeating it and to make the context. So suppose I make these parallel plates now horizontal. So these same parallel plates which we are talking about here, these black lines here, these electrodes I have drawn. Now you connect this to and there is vacuum in between there is vacuum. You connect this to a battery. What do you have? Let us say you connect this end to a positive terminal, you connect this end to a negative terminal. What you will get is positive charges here, you will get positive charges here like this, and you will get negative charges right here, corresponding negative charges, same amount of charge Q you are going to put in this case. What do you know? We know that capacitance in vacuum is equal to permittivity of free space of vacuum, that is the area of this capacitor and the distance between these plates. D is the distance between these plates, and A is the area of these plates, and suppose it will be very large. If that is the case, we also know what Q is. Q is capacitance times voltage. So I am going to take this A on here, A down here, and write this as in vacuum. In vacuum, what happens? The charge, what is the total amount of charge which is accumulated on the plates will be Q, that will be given by C times V, but I have writing Q by A, charge per unit area is what I am writing. So I am going to write capacitance per unit area, which I am going to write therefore as epsilon naught D times multiplied by V. That is the quantity I am going to write this, but V, the voltage, V is the voltage between these two terminals. This is the voltage V that we have applied. So this V divided by D is the electric field that I am going to write as epsilon naught E. So that is the electric field which you are going to get in vacuum when you do that. Now what happens if you take same parallel plate capacitor and you insert a dielectric between them? So, let us do that again. Now, you are going to insert dielectrics. Actually, let me be very clear. Let me draw it consistently. Let me draw these charges first. What I had in vacuum, I will add more to it. Now, what I am going to do is, I have inserted material, and therefore, I am going to write something here like this, let us say. What have happened? I have bound charges. When I applied an electric field like this, that means I connected the battery in same way as connected the battery here also the same way, which means I am going to get electric field in this direction. When I apply electric field like this, something happens. These bound charges, though they cannot conduct and hence material remains insulator, but it does polarize because of this field that we have applied. Consequence is, center of negative charge moves here, center of positive charge moves here, center of negative charge of this molecule moves here, center of positive charge moves here, negative charge here, positive charge here, negative charge here, positive charge here. That is what happens in the material which you inserted in. Consequence of that is, you are going to get extra negative charge here. Here is extra negative charge I am drawing, or maybe I use different color now for this. Here is a extra negative charge which comes about as a consequence of these. An extra positive charge here shown in square box which appears here as a consequence of this material which you have inserted in. So, what happens now? If I write capacitance, you very well know this capacitance in this case is given by epsilon naught, a dielectric constant times area divided by d. And now, if I want to write Q by A in this case, if I want to write Q by A in this case, then what will that quantity be is what we are wanting to write. This is dielectric. What will that quantity be? That quantity of course would be equal to, in same way, would be epsilon naught K prime d multiplied by, in this case we are going to write V, which we are going to write as epsilon naught K prime E. Remember this equation, we will come back to this. And now let us see what the total charge is. Now, in this case, what we are going to write is that this Q by A dielectric, we are going to write this as, this is surface charge. That is the total charge on the surface, or charge density, charge per unit area. We are going to indicate by sigma. That this sigma is, we are going to split in two parts. One as sigma vacuum plus sigma polarization, or I will use the color again differently. This was the red color charge. What do I mean by that? What I mean by that is that this black charge which you are seeing here, this charge is corresponds to this Q by A, which is sigma vacuum. You can write this as sigma vacuum. That is a sigma vacuum, and this is sigma, total sigma, what we are getting in total surface charge when you inserted dielectric. So, when it is vacuum, this is the charge which we had inserted, which is the black colored circles, these same black colored circles here. But when you inserted dielectric, we got additional red colored charge. This red colored charge, so the total charge sigma, therefore, now we get is what is due to vacuum plus something additional which we are calling as this polarization charges. So, if that is the case, then we are going to write this as equal to, this quantity as equal to epsilon naught K prime V by D as equal to epsilon naught E plus sigma polarization, due to polarization. What is this quantity V by D? Of course, is the electric field. So, we can write this as E0 K prime E as equal to epsilon naught E plus this quantity which we define as polarization, and hence I am going to write this P polarization, and this is the key term polarization, which will have a dimension of coulombs per meter square. This polarization is due to which something happens to our electrical behavior in a device when we insert a material in between the capacitor. It is this polarization which is responsible for something interesting. So now let us look at what this polarization is. The simplest model for P is, model for polarization is that we take polarization as proportional to electric field, and this proportionality constant, let us write it as susceptibility. So this quantity is dielectric T. All these ideas you have studied before also. If we take this model and we now insert this into this equation, then I am going to write epsilon naught k prime E as being equal to epsilon naught E plus epsilon naught psi dielectric E, which I am going to write as epsilon naught 1 plus dielectric times E, and now you can recognize this k prime is basically 1 plus susceptibility. So that is what this quantity is, dielectric constant of a material. All right. So this is where, this is something you had known very well. Now what I am going to do is something else. What we have so far assumed is that dielectric is ideal, non-leaky. What do I mean? What I mean is, we have assumed that this dielectric material is a perfect insulator. So in this capacitor, when you apply voltage, no current flows. In this capacitor, since this dielectric material is not leaky as vacuum, therefore when you apply electric field, there is no conduction whatsoever at all, and that is our ideal dielectric. In that case, we get some dielectric properties as measured by at microscopic level, what is known as polarizability, which I have not talked about, but by something called dielectric constant. However, what happens if indeed this material is mostly insulator, but it does give rise to some leakage current? What happens in that case? That is what we want to establish now. Now we want to establish how do we deal with such situations. Now I will introduce you to what is known as phasor notation. And this is something which you would have done before also. Suppose V is the voltage that we have applied, and it is a AC field which we have applied, and this field is equal to V naught, which itself could be a quantity, or is a V naught which could be a spatially dependent quantity, and let us use the e to power j omega t. That is the voltage we have applied. What is j? J is equal to -1, root -1. Some people prefer to use I instead of j. My preference is for j, but don't confuse, if you see I is the same thing. Remember, this will lead to a complex number. So this itself could be a complex number, this indeed is a complex number. So what is the voltage that we applied? The voltage that we have applied is actually V, which can always be generated by getting real part of V star, V complex. That is the voltage we applied. For example, if V0 is real, if V0 is real, then you can write V as equal to real part of V0, and this we are going to write it as cos omega t this V0 is real, then we can write V, this actual voltage, as the real part of, and I am going to repeat this one more time in context of Maxwell equation, real part of V0 cos omega t plus V0 j sin omega t, and if you take the, so this V therefore will be simply V0 cos omega t. So that is the voltage, AC voltage we have applied. So this is the phasor notation. So we consider this as the V voltage that we have applied. Then what happens to the capacitor? That is the question. So if I take a capacitor and you apply AC voltage, and I apply AC voltage, if you apply AC voltage of V star, then what happens? I get a current, I get a charging current, which will be given as dq by dt, which will be given as d c v dt, which will be given as c dv dt, and that quantity then will be equal to that quantity in time it varies as, remember, omega t. In time it varies as omega t, this V changes by omega t. So what would I get? I would get j omega c, and I will get back, since it is exponential, so I will get back V. That is what I am going to get. So charging current would be equal to this quantity. This current would be equal to this quantity, which if I want to write, I can write as equal to, I will continue here, which I can write equal to j, which I am going to take this j inside, and I am going to write this as omega c, and I am going to write this V, V naught e to power j omega t plus pi by 2. This pi by 2 appears because I have taken this, written this as exponential now. I have written this quantity as exponential pi by 2, j pi by 2. That is why this quantity is appearing here like this. What does it mean? It means that the charging current is pi by 2 off in phase from the voltage that we have applied. So if I draw this, and this I am assuming as an ideal, I am continuing to use an ideal capacitor right now. So what happens? So this is the, so if I draw this, the way I will draw it is like this. If I plot the real part and imaginary part, then this voltage, which voltage? This V star voltage which we are plotting would have a real part and an imaginary part. So if I draw that, then I am drawing this voltage V as V, this is the voltage V star, and the charging current that I get, would be pi by 2 off from this. This will be pi by 2 off from this V0 phase, and hence I will write this as current, I am going to draw it as perpendicular to it, pi by 2, this is I. Meaning there on this same plot I am plotting both current and voltage. So this is the current, this is for ideal dielectric. But remember, we started saying, what if it is leaky also? If it is leaky, then in that case we are going to write this I total, in that case we will write as this ideal I charging current plus some I loss. You can write some I loss. What do I mean? What we are saying is, if this capacitor this dielectric which was here was leaky, in that case, if it was not leaky, then we get a phase difference of pi by 2. If it is leaky, then we will not get a phase difference of pi by 2, but something else. So what we are going to do is, we will write in that case the charging current, which is dq by dt, as or total current, we will write it as the charging current, which is the current for an ideal capacitor plus some loss. So in that case, this red portion has to be shown. I charging is this current. If I show loss current as something like this, I loss current, then this total current is this current. And this is I loss. This is the loss current, and in that case we get this angle. Let us define this angle as an angle phi, and this tan phi or the loss tangent would be I loss divided by I charging current. Now what I am going to show you is that this behavior can be represented by, if we consider the dielectric constant itself as a complex quantity consisting of that same k prime, which was the dielectric constant, the real dielectric constant of a perfect dielectric, minus j times some k double prime, which is connected to this loss, which is connected to this quantity loss. So that is what this k prime is, k double prime is, and this charging current, which is for the ideal dielectric, was connected to what is this k prime. If we use this k prime, and we still will be able to work out what I have explained through a charging current in a capacitor, let us now do it in a more generic fashion as to what this loss term is. That is what our interest is, that if the capacitor is perfectly ideal, then we know what this is. But where does this come from? And that is what we are trying to understand, and let me do it in more general fashion by writing Maxwell's equations. The way we would write the Maxwell's equation, and this is something you might have seen before also, that assuming time dependence, again time dependence as e to power j omega t, as we had done, j again I repeat is minus 1. In that case, to be very well specific now about this phasor quantities, now we are going to write this E, let us say electric field, let us take any quantity, and let us as an example take electric field E. Similarly, you can do it for magnetic field or other quantities as well. So if I take this electric field E, then we know that this, we are going to write this as a function of space, that is position. Then E, actual real E, physically E, as a function of position and time can be obtained by taking real part of this E star quantity multiplied by E j omega t. It is the same thing which we did earlier also. Now I am doing it in a more generic fashion, and this of course is a function of position only. This is what the definition of a phasor is. In that case, the Maxwell equation, the first Maxwell equation, which is given as rho f, translates into, in phasor notation, translates into divergence of D vector in phasor notation. I am drawing this asterisk to indicate phasor notation as rho f, and the second Maxwell's equation translates as 0, and now the interesting ones, the curl of E, which is minus del B del t. Now the time dependence is coming, hence it is interesting. It translates into curl of this quantity E star, and remember what is the time dependence, what is the derivative of how would you take the derivative? Remember, time appears only as j omega t. So the time derivative we can write, and we will write as j omega. So of same quantity, since in exponential it will recover the same quantity. I am going to write therefore j omega. Whenever the time derivative del t appears, a j omega will appear because time derivative is taken in this form, of B star, and similarly curl of H is equal to j plus del d by del t which translates into curl of H star and now J plus J omega d star. Remember, this J omega again comes as del T, and since always time dependence is like this, so J omega shows up here. In addition to that, let us assume B star, not assume, this is the constitutive relationship, is mu prime times H star, means permeability, there is a magnetic properties, there is no magnetic loss, otherwise we would have written this quantity also as complex. So mu, that means we are taking mu as equal to mu prime, that means real, we are taking as real, whereas D we are going to write as epsilon naught times, now we are going to take complex dielectric constant K prime minus J K double prime times E star. And this we are going to write as epsilon naught K star E, and of course J is equal to sigma times E star, and this is the conductivity. I had used this sigma for also in this first slide, here I had used sigma as sigma for charge per unit area. So I am reusing the same symbol, I am going back here this sigma as, remember Ohm's law, where sigma represents conductivity. So here the sigma is representing conductivity, and I will not be anymore using sigma as charge per unit area. That was only in context of capacitor. So now we are going to stick to this sigma as conductivity itself. If that is the case, we are going to take this equation and it takes this curl. Let us take this equation and let us take its curl. What happens then? Let us write down that, therefore, curl of this equation, actually I am taking curl of this equation. In phase, since I am working phasor notations, I am taking curl of this particular equation. So curl of star is equal to minus J omega mu prime, and I am going to take curl of H. What I have done is, first for B I have substituted this quantity mu prime H, and I am assuming mu is not space dependent, it is a homogeneous medium, so it is not spatially dependent. So I am taking this out of the curl, and hence I am writing this as J omega mu prime curl of H. But we know what curl of H is, so then we write this also minus J omega mu prime, and we will write curl of H from here as J plus J omega D. D star, let us write as or let us write two more steps and then do it. This is this quantity. Now we will further expand this. This is equal to minus J omega mu prime. We will write this as sigma times conductivity times E, and we will write this as plus J omega epsilon naught K star times E. We write this as follows. Let us look at the left side also. In fact, we can write this as in free space, if then this quantity is 0. In that case, if I write the wave equation, then this is minus is equal to, I am going to write this as minus J omega mu prime sigma plus J omega epsilon naught K prime plus omega epsilon naught K double prime. These are all vectors. So if I miss, please keep that in mind. These are all vectors. So remember, I have taken K, I am writing K as this quantity as K prime minus J K double prime, because there is a minus J and multiplied by J, that gives me a plus here. So, I am going to write this further. So, I am going to write this as omega square mu prime and take epsilon naught also common. So, I am going to take epsilon naught common and another omega here. So, I am going to write this as if I take this omega naught, one omega out, omega naught out, I have taken this out. So, I am going to write this as k prime, and I am going to take one j out also. If I take one j out, I am taking this quantity out. If I take this quantity out, then I am going to get omega square epsilon naught, and j multiplied by j will give you -1. So, I am making +1 here, and I am going to write this as k prime. Therefore, what else? Minus, I am going to write this as j minus j sigma by epsilon naught omega plus k double prime E star. So, what do I see? I see this as some complex dielectric constant times E, and now from this wave equation, a minus sign here, and from wave equation we can recognize this quantity as being the permittivity equivalent to permittivity in free space, and that we are writing as this quantity as equal to, now you can see this is the real part if it was non-leaky, minus a complex part arising out of, this is because of DC leakage, this is DC leakage, and this is AC leakage, frequency dependent leakage. This is frequency dependent leakage. So, this is the loss part. So, this represents the loss part, the DC and the AC loss, and this represents the stored energy in a capacitor, and if there is no loss, it is perfectly non-leaky capacitor, then of course, this quantity will be 0, this quantity here would be 0, and you would have only stored energy part in there and nothing else. So, that is the general idea, that you can write a dielectric constant in form of a or permittivity in form of a complex quantity in which you have permittivity is k prime minus j k double prime, and this k double prime represents the AC losses. And of course, on top of that, because of this quantity j, you can also add, remember this is the displacement current. This is displacement current arises only because of time dependence, time changing electric field, and that is what this k prime is leading to. It is this current which is flowing, which is going to cause heat the dielectric, loss of energy that is due to k prime, whereas j, which is sigma times E, is a DC conductivity, and that is the DC part here of the loss. If both these quantities are 0, then dielectric will be perfectly non-leaky, All right. Now, with this definition we have got, now what I am going to do is talk about dielectrics and the mechanism which leads to polarization. So, this dielectrics, which may be lossy or may be non-lossy. If it is non-lossy, then then there will be some k prime, but sigma will be 0, sigma and k double prime. This sigma representing conductivity would be 0. And if it is lossy, then we will have either due to some DC conductivity or because of some AC conductivity, or the loss part of dielectric would lead to some energy loss. If that is the case, then let us look at either way. The dielectrics I am going to divide into two parts. One is linear and other non-linear. This definition comes from this relationship, that what is P what is the proportionality between P and E. Remember, if you go back, in some slides back, we had said that proportionality of P and E is given by this dielectric susceptibility. The question is whether this dielectric susceptibility is also function of E or it is not, or is it constant. Now, this is the question we are addressing now. If it is, if I is constant, then it is linear dielectric, and if it is not, it depends on E itself, then it is a non-linear dielectric. What I am going to cover now today is linear dielectric, and in the next lecture I will talk about non-linear dielectrics. So, this is with this, let us start looking at the mechanisms for polarization. The first mechanism we are going to look at is the electronic polarization. What is electronic polarization? It is a displacement of electron cloud. Meaning thereby, let us look at like this, something like this. Here is the center of positive charge, and let us say this is the electron cloud, this spherical form of electron cloud. This is electron charges, or the other electron cloud, and electric field is 0. What happens if you apply electric field? Let us say you apply electric field in this direction. What will happen if that is the case? Then your positive center of positive charge would move this way, and electron cloud may shift something like this. With its center somewhere here of electron cloud. In this case, the center of electron cloud and center of negative charges, that is, and the center of positive charge were coinciding, and therefore there was no net dipole moment. And since there is no dipole moment, therefore there will be no dipole. Since there is no dipole moment, therefore there is no polarization. Refer back, this was the dipole moment. When you applied electric field, what happened was center of positive charges, positive just shifted one way and negative charges other way. These are bound charges which moved relative to each other, and correspondingly they gave rise to dipole moment. And now you are looking at is that a situation E field is 0, of course there is no polarization, but once you apply electric field in this direction, then the two centers shift by quantity, let us say delta, and this leads to a dipole moment, and hence it leads to polarization. So, this is the mechanism of electronic polarization. This is the electronic polarization, displacement of electron cloud relative to the nucleus. This is a very important mechanism. Why is it? It operates till very high frequencies. On order of 10 to the power 15 hertz. So, it can operate till, and then it drops off, and then after that it drops off. So, all the way from low frequencies to high frequencies, this quantity, this mechanism is able to operate. Second point is that it does not involve hopping of ions or atoms. Hence, it is not diffusion like process, hence it is temperature insensitive. In this course, I will not do the mathematics of this, I will simply tell you what the different mechanisms are. So, this is the base, this is a quick overview of what electronic polarization is. Let us move on to next mechanism, which is ionic polarization. And now, as the name suggests, it is displacement of ions when you apply electric field. and this picture will give you idea what I mean. Let us say this is negative charge, ion, positive ion, negative ion. Let us draw a few more. Here is the ionic crystal, and now we apply some electric field. Let us say we apply electric field in this direction. What happens in this case? So, if you apply electric field in this direction, so positive charges are going to move and negative charges are going to move. So, so we can write something like this then. If I draw this, this is a positive charge which has displaced slightly, and negative charge which has come here, and positive charge which has moved away, and a positive charge is moved here, away, and negative charge which is here. So, the whole negative charge, this sort of has moved down, and the whole positive charge has moved up slightly. As negative charges have moved down and positive charges have moved down, and sorry, I am messing up. The negative charges have moved down and the positive charges have moved slightly up. As a consequence, now you are going to get a net, as a result of it, you are going to get a net if you look at the center of positive charges and the center of negative charges, which is right here, this is the center of negative charge, this is the center of positive charge, and there is a displacement between them, and this leads to, this is equal to 0, and there is some E field leads to polarization. It leads to polarization. This mechanism operates in a frequency range of 10 to power 12 to 10 to power 13, all the way up to 10 to power 12 to 13 hertz. It can move up, operate up to that. Remember, electronic polarization could operate up to 10 to power 15. This mechanism operates up to a frequency of about 10 to power 12 to 10 to power 13 and then drops off. So, if you go to frequency 10 to 15, you will only see electronic polarization. If you are operating up to frequency of 10 to power 12 to 13, you will see both ionic polarization and you will see electronic polarization. Both these mechanisms will be applicable. Second point, this is also temperature insensitive, because again there is no hopping of ions or atoms. Now, let us move to next one, dipolar polarization, and this I am talking about more because tomorrow's lecture or next lecture, the 20th lecture, we will talk about non-linear dielectrics, and this mechanism play a major role there. Just to say, frequency of operation is up to about 10 to power 10 hertz. This is the frequency up to which it is able to operate, and there is hopping of charges, hopping of ions, hence temperature sensitive. This is a very temperature sensitive mechanism, which we will see in some non-linear dielectrics. We will see this mechanism playing an important role. So, the way one can explain is that suppose you had two different polarization sites. Let me plot like this. Let us say some coordinate system, some position coordinates of at ions, and here I am plotting energy. Suppose there are two equivalent energies possible. That means if this energy curve is something like this. So, there is two minimums possible here, then you can have equal preference for sitting on this side or sitting on this side, and this is the activation barrier between them. Let us say this is the EA activation barrier. Question we ask is, what happens if we apply, if there is a dipole moment, one let us say corresponds to a dipole rotating in the direction of electric field, and one totally away from it and totally with the electric in the direction of electric field. Then what happens? You apply electric field. You know that if you apply electric field, if there is a dipole moment is mu, is a dipole moment, and we apply electric field, then dot product of dipole moment and electric field gives us the energy, or minus the minus sign here, which is equal to mu magnitude E cos of theta, where if this is the electric field and this is the dipole moment direction, then this is the theta between them. If that is the case, so if for theta equal to 0, we get u as equal to minus mu E, whereas for theta equal to 180 degrees, we get u as for theta we get missing a minus sign here, and this will be mu of E. Then between these two positions, delta u could be equal to 2 mu E. This I can show if I apply electric field, then you could have this picture changing over to one side becoming more preferred than the other side. That is, this barrier reduces by amount EA minus mu E, whereas this barrier increases by amount EA plus mu E, plus mu E. Now, if you look at this picture, when I had applied no electric field between two polarization directions, there is equal probability of ions hopping from here to here or hopping from here to here. The rate at which ions hop from here to here would be same as rate at which ions hop from here to here, and there will be no net polarization. But now, with dipole directions different between this side and this side, if there will be greater preference for ions to jump from this side to this side than from this side to this side, and hence I am going to get net dipole moment. And because of this dipolar mechanism, we get therefore a dipole moment, and because net dipole moment when you apply electric field, and hence a polarization, and hence a dielectric behavior changes. Last one was also a space charge polarization. Let me see if I have given you the frequency domain in which this operates. Yeah, I have written 10 to the power 10. So, space charge, this can operate at very low frequencies, and really related more to electrochemistry and double layers, relates to double layers, and is not of that great value in solids. It is more interesting in case of solid surfaces and liquids, where you may be familiar with the surface getting charged. Let us say it is a positive charge on the surface. Then what happens is, then if you have a liquid on this side, then they form, all the negative charges form a stationary layer here. So, this liquid then acquires a net positive charge, then it acquires a net positive charge, something like this then. But there is a net positive charge. Ultimately, far away, the number of negative and positive charges become same. So, what you get is a net charge here, a charge region, and capacitance of this double layer. There is a capacitance associated with this double layer leads to, or is related to, leads to space charge polarization. So, these are the various mechanisms which operate. Finally, let me show you how this, therefore, if I plot k prime, this is the dielectric constant versus frequency, then what we have said is, let us say this is 10 to the power 0, 10 to the power 2, 10 to the power 4, 10 to the power 6, 10 to the power 8, 10 to the power 10, this is log scale, 10 to the power 12, 10 to the power 14, 10 to the power 16. Let's move this f here. This is the frequency. Then what we've said is up to 10 to the power 15, this mechanism, electronic mechanism operates. Somewhere here up to here, electronic mechanism operates, and this is what we are showing you here. This is the electronic mechanism. So, if I look at this somewhere here like this. This is electronic, due to electronic reasons we are having this K prime due to electronic reasons. Then if you go to lower frequencies, slightly lower frequencies, then up to about 10 to the power 9, I am going to draw something like this, and I am going to smoothly join this, something like this and something like this. Then this region up to here, this is the next, which is ionic polarization. So if you are up to this frequency, then both electronic and ionic polarizations contribute to K prime. Then if I go further somewhere here, then dipolar somewhere up to here operates the dipolar. This is now dipolar, and then finally the space charge polarization, which is something like this. This is the space charge. This is the space charge polarization, and correspondingly if I plot K double prime, then wherever these changes occur, somewhere here you are going to get a peak. This I have not talked about. There are relationships which based on which you can calculate these, but I am not going in that much detail. You will get K prime. Remember what K prime is. K prime is about loss, and K double prime is about stored energy. That means stored energy would be equal to, if you since do half CV square, integrate over time period, then you will be should be able to show that this will be equal to epsilon naught K prime E square would be the stored energy, and the stored energy and lost energy would be equal to half omega epsilon naught. We are going to write this as K prime double prime plus sigma. This is the DC part, this is the AC part, this is the DC part, E square. This is the lost energy. And just for your, if you have ever wondered why does microwave ovens work, it is this: when you apply AC frequency, water molecules are made to rotate, and this polarization is not able to keep up with the rate at which the electric field is switching directions. If they were able to switch, the polarization was able to switch at the same rate as the electric field, then we would have had only this K prime, and we would have all stored energy. But because it was not able to follow it, and hence the phase difference emerges, and you start getting a loss. And this quantity is the quantity which is the lost energy, which appears as heat, and water starts boiling, you can cook your food, etc. It is because of this energy which is why this is happening. And last slide, which I will show you some, I will leave you with some values. This tan delta is the lost tangent, is basically K prime by K prime, assuming K double prime is much larger than sigma by omega epsilon naught. In that case, we define this as lost tangent, and some materials, important materials, alumina, a dielectric constant of 9.4, and is a lost tangent. So you can heat this a little bit. MgO, silicon oxide, a very common material in electronics, TiO2, zinc oxide, aluminum nitride, diamond, silicon has a very high dielectric constant, and this material is what we are going to start focusing on in the next lecture, which is a non-linear material and has a huge dielectric constant, and it's also a piezoelectric material, and these are the material we will start looking at as non-linear dielectric. To explain what a non-linear dielectric is, that we will do in the next lecture, but I hope this gives you a quick overview of what dielectric materials are. Thank you.